For standard 1.2, I chose to do question 1.13 from our textbook. The question asks us to consider a quantum system with an observable A that has three possible measurement results, A1, A2, and A3. Part A asks us to write down three kets, A1, A2, and A3, corresponding to these possible results using matrix notation. So, part A, I have written down all of our three kets, and we represent a ket as a common vector containing three coefficients that multiply each basis ket. The CNs are the unknown coefficients of the eigenvector AN corresponding to the value AN. For part B, it asks us to consider a system that is prepared in the state shown below, right here. And we want to write this in matrix notation and calculate the probabilities of all possible measurement results. So in matrix notation, our system is written as a column vector. So the eigenvalues in our system become all the elements in our column vector. So this is what we are left with. So as you can see, all the eigenvalues are the new elements in our column vector. So next we want to calculate the possible measurement results. We need to normalize the state vector. Alright, so first we have to normalize this. And so we want to take the inner product of our column vector with itself, but we need it to be a bra. So in order to, right now we have the matrix notation for our ket, which is a column vector. So we need to take the adjoint of our column vector representing our ket in order to get the bra side of the inner product. So we are left, once we do that, we are left with this. So when we take the adjoint, it transforms our column vector into a row vector, and all the elements become the complex conjugate of the elements that are in our column vector. And again, when we normalize, we introduce a normalization constant C. So again, take note, I have introduced a complex conjugate or complex normalization constant C and found the bra side of the inner product by taking the adjoint of the AN column matrix representing the ket side of our inner product. So next, the rules of matrix algebra can be applied to find an inner product. Thus we have 1 equals the modulus of C squared times this. Plugging in our values for A1, A2, and A3, we get this, and we do some basic algebra, and we find our normalization constant is 1 over square root of 30. So this makes our state vector this. So this is just our normalization constant C multiplied in front of our column vector. So now we can use this to calculate our probabilities. So up top we have the equation to solve for our probability for our A1 measurement. So this is just an equation. I got the book. It's the inner product of the bra of A1 and the ket of our systems. So going through that, we get we can pull our normalization constant out, and it becomes 1 over 30 since we're squaring the inside of this. So pulling that out and forming matrix multiplication and then squaring it, we get 1 over 30. Using the same technique for the A2 measurement, we get 4 over 30, and then for our last measurement, A3, we get 25 over 30. So here is a histogram of our results. Part C asks us, in a different experiment, the system is prepared in the state, just shown right here. Write this in matrix notation. So we have this written in matrix notation, and calculated the probabilities of all possible measurement results of the observable A and plot a histogram of the results. So first we normalize using the same technique, taking the inner product with itself, is n equal to 1, we get a normalization constant out front, and we solve for C, and we get 1 over the square root of 13. So this here is the equation for our normalized system in matrix notation. And going to the next one. Calculating our probabilities, we use the same technique as before. So our probability for our A1 measurement is 4 over 13. Our probability for our A2 measurement is 9 over 13. And here is a histogram of our results. And this is my standard 1.2.